see that the doping has distinct effect on oxidation resistance of different metals, and we see that in case of zinc oxide, if we have lower valence lithium, then the oxidation resistance will go down, or if we have higher valence aluminum, the oxidation resistance improves. And it would be reverse in case of nickel, where lithium leads to improvement in oxidation resistance, whereas chromium decreases the oxidation resistance of nickel, or the oxidation resistance power of that nickel oxide on top of nickel. The same thing also relates to iron, where iron oxide FeO is a p type oxide, and there also if you have more chromium, it decreases the, if you have chromium doping, it decreases the oxidation resistance, but once it reaches to a certain limit, for example 18% chromium, instead of having a doped structure, we have a chromium oxide layer, which actually improves the oxidation resistance. So, the doping effect will be effective up to a certain limit, maximum around 5%. Now, in order to improve the oxidation resistance, there are few more techniques, and most of them are basically alloying related. For example, if we have molybdenum or tungsten or niobium in iron, then the oxidation resistance improves, as well as the creep behavior improves at higher temperature. But if we would like, if the oxidation resistance is to be improved, and if the iron operates at around 1200 degrees Celsius, then the alloying is basically done with there will be a coating, which is actually metal, then which is basically, for example, one coating that is M, Cr, aluminum and yttrium, and here this is either nickel or iron or cobalt. So, this coating can give a very good oxidation resistance at 1200 degrees Celsius. Even sometime boron containing silica glass, that can also give a very good oxidation resistance. So, this is about oxidation, but there is one more corrosion phenomena, that is called hot corrosion. So, the hot corrosion, so it is actually a degradation process rather than corrosion, because already if we have oxides, and due to the reaction with the ingredients in the environment, the oxide layer transforms to a different scale, and that scale would be non-protective. For example, in case of turbines, gas turbines, where we have, if we see the gas turbines, so ingress, there will be air which is coming in, and then it will be compressed, then mixed with fuel, and then this will be ignited, and then the temperature reaches around 700 degrees Celsius to 1400 degrees Celsius. This is gas turbine. Now, there at that high temperature, the sulfur would be present in the fuel, and that sulfur would lead to degradation of that oxide, which is forming on the surface, and which gives actually protection of the turbine blades and the total turbine structure. Now, if we see that if this turbine blade, gas turbine is operating in the sea environment, there we have sodium chloride. So, the sodium chloride, if we have sodium chloride and then also sulfur in the presence of oxygen as well as H2O, there could be a formation of sodium sulphate. So, sodium sulphate would be a possibility. So, there could be a product of Na2SO4 plus HCl. If we balance it, then this will be 2, then this would be 3 by 2 H2, and then this goes to 2 HCl. Now, this is the reaction that can happen inside the turbine, and this one has two components. One is acidic and another one is basic, which is Na2O and SO3. So, this is acidic and this is basic. Now, if we have oxide MO that can react with acidic part, basic part, which is Na2, and it can form M2 plus M2 plus this would become MO 2 minus plus 2 Na plus. So, we see that the oxide layer is becoming non-protective because it is forming iron, and then again this one can react with acidic part, it can form M plus 2 plus SO2 2 minus. So, again we see that ion formation. So, the oxide is losing its protective nature. So, this is actually the hot corrosion effect, and this one, this plus NaCl, they can form low temperature eutectic. So, that would be also not good. So, this is basically the hot corrosion, which you can see, we can see that it is not a corrosion effect, where we do not have any oxidation or reduction process, rather it is actually this one converts to a non-protective scale. Now, we discuss corrosion testing and corrosion rate measurement as well as failure analysis. So, corrosion testing and failure analysis. Now, in order to measure the corrosion rate of a particular metal or alloy, we need to know how we would perform the corrosion test. But before that, we need to know what are the purpose of why do you want to go for corrosion testing for a particular metal or alloy. Now, the purpose of corrosion test, one, definitely evaluation, it will help in evaluation and selection of material response to some corrosive to the environment. Of course, we need to know the corrosion response as well as its corrosion rate in a particular environment, so that we can choose that a suitable material. And then and of course, it would be specific for application too, corrosion environment as well as application. Then second would be evaluation of new and old metals and alloys to determine the environment in which environment they would be suitable. So, suitability of metals and alloys whether new or old in a particular application, in a particular environment. For example, in case of new, we need to see its response. At the same time, for old, how long it will offer it in that particular application, exposed to the environment. That application is exposed to the environment where it is working. Then we can also think of controlling corrosion of metals and alloys. Then finally, we also need to know mechanism of corrosion. For this is for research development. So, these are the for these we need to go for corrosion testing. Now, how many ways we can do corrosion testing? There could be corrosion testing. Actually, we need to know what is the rate first thing. The thing that comes into our mind, that is the corrosion rate measurement, and we can do it in different ways, and the rate measurement should be also done in house. That means, where the material will be subjected to application or operation, or we need to also perform some test in the laboratory for either research and development purpose, or the preliminary assessment of the corrosion rate of a new material, let us say. So, that case preliminary assessment will guide us that whether out of 10 materials, which material will be suitable for that particular application. So, corrosion testing can be divided into 4 types. So, corrosion testing can be divided into 4 types. So, one is laboratory test. In case of laboratory test, definitely as discussed, it is basically a simulated environment in the lab, and then we have of course, when we perform the test, that time the sample size would be small sample, and of course, the small number of number would also be small. And then we have pilot plant test or semi work test, and in this case also we can incorporate let us say 2I, 2, we can also incorporate field test. So, in this case what we need to do here, of course, that material will be subjected to a small scale operation, and then there of course, one would be large number of samples would be considered, and that time either that can be exposed to a service condition or may not be exposed to service condition. So, then we have coupons, actually a small coupons that can be placed in a rack in a particular fashion, and time to time we can take those samples out and we can see what would be the corrosion response. Then we have actual plant or actual service tests. Service test here, of course, this is a real condition, of course, and this samples will be materials will be under subjected to service mode, and that means that would be in operation. Then for example, one example is the tube. Let us say you have a iron tube and some tube where you have some corrosive which is going through, and that time we can place some sample, and that sample corrosion rate can be judged in the real condition. Then pilot step, of course, and before coming to this plant test, we need to perform this two tests. One is laboratory test and the pilot plant test. If we have a large number of options, then these two tests will narrow down those options, and then finally, we are left with a very few options. So, out of those options, the plant test will decide which material would perform in that service condition better. So, these are different test methods, laboratory test routes. Now, if we consider how we can perform these two test routes, of course, one is exposure test. Then this can be also broadly categorized into two sections. One is exposure test, and second one is electrochemical test. And in case of exposure test, this is the simplest one, where we have some test space, and that test space we exposed to the environment, and after a certain time frame we will take that sample out and see what is the weight loss. So, if we see the weight loss is del W, then del W divided by the area and then the time, this would give the corrosion rate of that particular material in that particular condition. So, exposure test, of course, we need to follow some standard. So, one is the conditions for exposure test, specific test method, test methods, and those test methods can be found out in different standards, either ASTM or NASA. So, those test standards are to be used, and then also we need to know how long, and this test standard will tell us how long one material is to be exposed to a particular environment, what would be the sample size, what would be the sample dimension. Then of course, we have few conditions. Let us say we are hanging, let us say the samples are hanging in some different angles. For example, if we put it in the environment at a particular angle, the angle at which it is interacting with the environment, that is one critical issue. Or it could be velocity of that environment. So, one is angle, velocity, then of course, proper insulation, it means, let us say we are exposing, let us say the sample is exposed to the environment by hanging from a station. So, that time this part it should be insulated, and if this is basically the from which it is being hung, that is a metallic object, then there should be this connection should be properly insulated, otherwise there could be galvanic effect here. And here is the sample, this is my sample, but if it is, and also this one in this part also we have 2 metal corrosion. So, this part should be properly insulated, otherwise there would be galvanic effect related galvanic effect. So, there wrong information will be obtained if we do not insulate do not have proper insulation. So, this is exposure test. Now, coming to the electrochemical test, which is very important, and this will be discussed in little this will be discussed and this will be elaborated little more. And if we come to the electrochemical test, there are 2 methods by which we can calculate the corrosion rate. Electrochemical methods. Electrochemical methods, we have 2 broad category, 2 methods available. One is Tafel extrapolation, and the second one is linear polarization. Now, if we come to the Tafel extrapolation, so in this method we need to polarize the sample in a particular solution or the environment to the positive side as well as negative side from the corrosion potential, free corrosion potential, and then we need to draw a Tafel slope, and where those Tafel slopes are connecting, that point would be the point of interest. There we can determine what is the corrosion density, current density at that point, and we from that we can find out what is the corrosion rate. Let us see, we have already discussed a lot on Tafel equation and the plots. So, those plots will be useful. Let us see how we can find out corrosion rate from Tafel extrapolation. We know that these equations anodic over voltage would be equal to beta A log I A I 0 for anodic reaction, and then we have cathodic over voltage, which is beta C log I C, which is current density corresponding to cathodic reaction I 0, and this C is actually the for the cathodic reaction, which is exchange current density of the cathodic reaction on the metal surface. And this is negative and this is also negative. So, both the negative things are considered in this equation. Now, if we plot it, so this is potential and this is log I, and I is the current density. Now, for a particular metallic corrosion, let us say the zinc in HCl, we have zinc anodic reaction, and for zinc we can also consider what is the cathodic reaction for a single electrode system. That time this is my E A, which is equilibrium potential of that particular single electrode system, zinc system. That means, this is zinc plus 2E zinc, this indicates this one. So, For this reaction only this is considered, and this is my I A, I 0 which is anodic current density of zinc plus zinc on zinc surface, and we have hydrogen evolution reaction which is the cathodic reaction. We can consider this is my E C which is equilibrium hydrogen potential, and this is my I 0 of hydrogen reaction on zinc surface. This is the cathodic polarization, and this indicates this, and this one indicates this. So, the two lines are drawn from this concept of Tafel equation, and then if we have zinc dipped in HCl, the potential of the zinc will be at this point, which is the corrosion potential, because it will reach to a new equilibrium state, and the corrosion would happen as per this current density which is I core. Now, the potential after some time it will, the potential if we measure the zinc electrode potential, if we see, it will show this potential. Now, from that potential we have to take to the positive side as well as negative side, and we will get a curve. So, if we let us extend this line in dotted fashion, now from this potential if we extend to the positive side, taking it to the positive cathodic side, anodic side, and then also negative side, then we will get a curve like this. So, this is the nature of the curve, and this line actually meets this straight line part. This is the straight line part. This actually if we extend it, this line will meet, this line will meet this straight line part, and here also if we extend it, this line will meet this linear part. Now, rest of the actually we will see this line only, this yellow line only, the graph will be this yellow line only, and where these two lines are hidden. Now, if we, and this is the straight line part, see if we extend this straight line part, if we extend this straight line part, have extended with the red one, and this part, this straight line part, if we extend it, so this is the point we would get, and this is actually nothing but I core. Now, once we know I core, then we would definitely get the knowledge of the corrosion rate, and of course, this line indicates zinc, or if we consider general purpose, this line indicates metal ion formation, and this one indicates hydrogen gas generation, which is the cathodic reaction. And once we know this point, we can easily calculate what could be the value of I core from the graph, as well as we can also find out if we know the pH of the solution. Solution pH, if we know, that can also give you give us the value of this. And from the metal surface, if we know what is I 0, now we can have a small equation which is E c. If we draw this, if we find out what is the equation for this, that is basically this one, and this we can write as E c corrosion. This is actually, this value is E cor. So, E cor minus E c equal to beta c log of I cor by I 0 c. Now, I cor is also falling on the line. I can put that I cor in that equation instead of I c at this point, and this is my over voltage, cathodic over voltage. Beta c we can calculate for that system. I 0, if we know, we can also find out what is I cor. So, one way, if we can have this Tafel slope and find out from the graph, or other way around, if we find out what is the corrosion potential, that time if we know the pH value, we can find out what is the E cor. Now, let us extend this equation. E c is also found out from this. This is H plus H 2 mass plus R T by F, which is 1 Faraday, into 2.303 log H plus ion concentration in the solution, and then at 25 degrees Celsius and 1 atmosphere pressure, this value goes to 0, and this would become minus if we consider the pH of the solution. So, E c would be equal to minus 0.059 into pH. So, minus log of H plus ion concentration is nothing but the pH. So, this is the equation for E c. We put this here. So, the final equation would become E cor minus, which would become plus 0.059 pH would be equal to beta c log of I cor divided by I 0 c, or c in this case is actually H plus half H 2 or 2 H plus H 2. So, this is the equation. From this we can find out what is I cor, and if we know I cor, we can find out what is the corrosion rate of that metal in that particular solution. And this is a relatively quick method compared to the plant exposure, but it actually does not give the actual response of the material in the application, in actual application, but it is advantageous because immediately it can give you initial idea about the corrosion rate of that metal in that particular solution. Now, it has also a certain limitation. For example, when we consider if we consider the limitation of Tafel extrapolation. So, if we consider limitation, one is when we consider, let us say, zinc in HCl, this is zinc in HCl, we assume that the entire surface, on the entire surface we have let us say the area is A0, the entire surface we have cathodic as well as anodic reactions. But actually some part of the this area would be cathodic side, some part would be the anodic side, and let us say the only the half of this part is, if we consider statistical uniform distribution of those two reactions on those sections. So, if we consider that this is my cathodic side and this is my anodic side. So, we have only half part which is getting dissolved, because the cathodic part will be protected because of the cathodic reaction that is happening on this part, but only the anodic side will get corroded. So, actually it gives it actually the corrosion rate is actually half of the corrosion rate what we are measuring from this route, because there the assumption is the whole area is active as anode. So, we are getting a double corrosion rate than the actual. So, that would happen, and depending on the area ratio of cathodic and anodic would have less corrosion rate. Practical rate would be less compared to the theoretical experimental rate what we are finding out here from the Tafel extrapolation. Other limitation would be, now when we are considering this gaseous reaction as the cathodic reaction, then the crux of this method is getting this linear part in the graph, polarization graph. This is my polarization graph. In that part, this should be linear, that should be linear part. If we do not have this linear part, then there is a problem, because we cannot extend it and then find it out where we have, because this E c we can find out from the pH. So, it has to be connected and this straight line should pass through this point, but if it is not straight and linear, then we have difficulty, because there could be a possibility of concentration over voltage. So, before reaching to this linear part, before that it can bend down and it can become concentration controlled. So, in that case this is the linear part. See, if we extend like this, we will not reach to this point. So, that gives you a wrong result. The another possibility, there could be resistance polarization, that might also lead to a problem in getting this linear part. So, these are certain issues with this Tafel extrapolation, but most of these limitations can be avoided if we go into the linear polarization side. So, the linear polarization, let us discuss what could be the linear polarization. Now, whenever we come to the linear polarization, that is based on the basic principle. The basic principle is as follows. Now, if we consider a point which is the potential, let us say this is the potential axis, this is E axis and this is the current axis, I axis. And if we see that the potential of that metal is at this point, which has some value, let us say E 0, rather let us put E dashed. So, this is the potential at this point. Now, if we go towards the positive side from that potential, which is basically the new equilibrium potential, and in case of corrosion, it is the corrosion potential. Now, that time if we go to the positive side or negative side, if we go positive side and if we go the negative side with respect to the absolute current density, it is not the log of current density, rather absolute current density, then we see the graph would be like this. Graph would be like this. So, that time if we have this graph, then we say that there is a very small region. In this region, we have this line is linear, and this is the voltage where this part is linear, that is around here it would be around 10 volt, 10 millivolt, and here it would be around 10 millivolt. So, in this region it is linear, okay, and from this linearity the slope can give us the indication of corrosion rate. the slope of this line. And this is actually the basic principle of linear polarization, where we have to go to the positive side or polarize anodically as well as cathodically within the narrow band of 10 millivolt or so. Potential versus current density would be linear within that narrow range of 10 millivolt in the positive side as well as negative side, and the slope of this line, which is actually del E versus del I, would give information about I core. So, once we know I core, we can find out what is the corrosion rate of that metal. Now, in order to understand better and how we would get to this linear part, let us find out what is the basic structure, how come we get to this particular linear part, and for that we need to use the help of Butler-Volmer equation. Butler-Volmer equation, and that equation says that this is I equal to I 0 exponential alpha n f r t minus exponential minus 1 minus alpha n f by r t. This is my over voltage. The current density, which is actually the I applied current density, is the difference between I A minus I C or other way around. So, this is for cathodic anodic polarization, and this is for anodic, or it could be I C minus I A. So, this would come in the front. So, this is the equation for Butler-Volmer equation, and actually the Tafel equation is coming from these two equations. The Tafel equation N A equal to 2.303 R T by alpha N F log of I A by I 0, and whereas C would be equal to 2.303 R T 1 minus alpha N F log of I C minus by I 0. Now, from this beta A is nothing but this part 2.303 R T by alpha N F, and whereas beta C is minus of 2.303 R T 1 minus alpha N F. Now, here R is the gas constant, T is the temperature in Kelvin, N is the number of electron that is associated with for the metal reduction or oxidation, F is 1 Faraday, alpha is the symmetry factor, and these are the Tafel slopes. This is for anodic slope, this is cathodic Tafel slope. Now, we see that if we would like to, if we plot for a single electrode system, if we plot what would be the cathodic and anodic polarization with respect to log I, then over voltage, if we plot, the plot would be like this, and this is 0, this is positive, which is anodic, this is negative, which is cathodic polarization, and this gives you by this indicates this line, which is for cathodic reaction, and this line is or this anodic reaction. Now, here we need to consider what would be the plot, the same plot if we would like to draw with respect to current density in absolute scale, not the log I, and over voltage. What could be the plot if we take it to the absolute potential versus I plot. So, if we see this is, and of course, this is nothing but I 0, this current density corresponding to this point. Now, if we plot this, then the plot would become like this. Plot would become like this, where this is in near over voltage positive side, and this is over voltage negative side, and this is 0 over voltage, this is I plus, this is I minus. I plus and I minus means this is actually the anodic current density, this is cathodic current density. So, that means, this when we consider this line, that time we consider the cathodic current density, which is I c, this is my I a. So, if we go from 0 over voltage to a positive side, my potential over voltage versus current density plot would be like this, and vice versa for the cathodic side, this would be like this. So, in this case anodic current density, cathodic current density would be the governing factor at a higher over voltage, because we have seen in the case while we discussed and this has already been discussed, that at higher over voltage this part, the I c part on this side would be negligible, and higher over voltage on the cathodic side, this anodic current density would be negligible. Now, how would we see? It is fine that we have anodic and cathodic polarization, but how would we find out what is the I 0? Now, as we know that higher over voltage, so over voltage is I applied would be equal to I a minus I c if we consider this side. Now, at a higher over voltage, in this case we have seen that this point is negligible. So, it would be becoming I a, but there would be this component also, and this is coming from this and this part. So, if we individually if we plot I c part, this is I c part, this is my I a part in addition to I 0. So, I a equal to I 0 exponential alpha n f r t over voltage. This is my I a, and I c, of course, if we add I 0 here. So, this is my I c. So, I am not putting that I 0 part, I am just keeping it within the bracket. So, I have taken this I 0 out. So, that case the plot would be for I c, the plot would be, in this case plot would be like this. It will finally match with this, and same thing for I a, plot would be like this. Now, we see that at higher over voltage, and this is my I c, this is my I a, and this part, this is I applied, which is the overall current. Now, in this case we find that at higher over voltage I c contribution is less, is negligible, and that is what this will be only the I a part, and higher cathodic over voltage side, the anodic current contribution to the polarization would be negligible, and only the I c part will go for the polarization. So, our concept of polarization is fulfilled there, and these two points these 2 points, if we find out the value at these 2 points, this is same as this is, let us say, I double prime and this is I prime. So, I double prime would be equal to I prime, and we see that in this case this line passes through I 0, that means the IC line passes through I 0. This is my IC line. So, IC line is passing through this current density, which is I dashed at 0 over voltage. This is also 0 over voltage. So, this would be equal to I 0, and same thing if we consider this one, that time this IA line is passing through I 0 at 0 over voltage, IA line is passing through 0 over voltage at this point. So, this is equal to I 0. So, over voltage as well as current density both are fulfilled, and once we see this, if we consider this particular part a very small over voltage, that time this part is linear. This can also be proved, where if we expand this part, these two things, considering this is to be very small, and then we will find out that the, if we expand exponential part, we will see that this becomes I 0 N f over voltage by R t. So, if we expand these two things, and then we can get to I 0 N f neta by R t, which is this part, which is linear. That means, over voltage is linear to the applied current density. So, this is happening on a single electrode system, but in case of corrosion we have one cathodic, one anodic. So, the same process is happening for cathodic side as well as anodic side, and that would lead to the concept of linear polarization. So, if we would like to plot the cathodic and anodic cathodic and anodic polarization with respect to potential versus current density, then we can get to the linear polarization part. So, this is my, let us say, this is my cathodic side, this is my anodic side, and let us say my corrosion potential is this. So, if we compare the linear electrochemical polarization Tafel extrapolation, we got a plot like this, and this is two linear part, this is E core and this is my I core, and this is my cathodic polarization, this is my anodic polarization. So, same thing would like to consider here. This is E core, this is potential axis, and this is my current axis. So, on this line, this is the point now which is E core, which is nothing but this. And if we consider the cathodic polarization, it would be having like this, and where we have these are the two lines, and this is my IA, this is my IC for the cathodic reaction. So, actually we are considering M plus H plus going to M 2 plus 2 H 2. So, this reaction if we consider, this is my cathodic reaction, and this is my I 0 for hydrogen evolution, and the same way we can also think of anodic side, where this side is nothing but metal dissolution, in the same way as we have discussed in case of single electrode system. Now, this part is metal deposition, and similarly we can find out what is the I 0 for this reaction. So, this is my I 0, I 0. Now, so this we can extend like this, this we can extend like this. Now, this line, if we draw a mirror image of this line, we can have a plot like this. We can have a plot like this. This is this line actually the mirror image. Let me draw it with the yellow color. So, if we draw a mirror image of this, so then this rates of this cathodic reaction and anodic reaction would be same at E core. So, this is the point where anodic reaction rate and cathodic reaction rates are same, where I value for both the reactions are same. Now, this point also would pass through this particular junction point between this line and this line. Why? Because at this point we see that I A for this is my I A and this is my I C, because this part is mirror image of this and this is my I C for the cathodic reaction. So, I C equal to I A, and that time what would be, and this would be nothing but I core, since this is the point which is I A equal to I C equal to I core. The same thing we are plotting with respect to the potential versus I plot, rather log I. Here we have log I, this plot is E versus log I. Now, we see that these 2 points are meeting at this point, and this is my I core, and where I A equal to this is my I C, I A equal to I C equal to I A equal to I C equal to I core. Now, if we consider a small over voltage from this point, that means from this point if we go a small positive side, so we can have a, let us say, a small over voltage which is del E, that part this small triangle is forming, where this line both line can be considered as linear, because it is a small over voltage. Now, if we extend this triangle, so this is my triangle, this is my triangle, this is, let us say, this is A, B and C. So, this is C, B, A, and if I draw a normal from this point to this line, we have 2 triangles, and this is basically 90 degree. Now, we have 2 lines, let us say this slope is S. So, we see that 2 triangles are forming, and these are 90 degree after drawing the normal. Let us say this point is D. Now, if we consider slope of this line is S A, which is nothing but the slope of anodic reaction line, and the slope of the cathodic reaction line, which is S C, then we can also find out what is the S C and S A from this dimension. And S C would be equal to this by this, and S A would be equal to this by this. Now, if we consider the overall current density, overall current is del I, and if we consider this is to be x, then we can find out from geometry what would be S C and what would be S A. Find out what is S C here. So, S C would be equal to d E by d I, because this is my E potential and this is my I. So, d E d I, this is for cathodic, it would be equal to del I minus x by this is del E, because this is my del E. We have seen that this is my del E. So, this is my del E. So, this is basically del E divided by del I by minus x, because this part this by this. Then again we have S A would be del E by del I for anodic, because if we come to this graph, we see that this is for the anodic reaction, or we can say that this entire thing is for M plus 2 plus 2 E M, and this is for with respect to this reaction, this for H plus 2 E H 2. So, this is for reverse reaction and this is for forward reaction, and in this case this is for this reaction and this side is for this reaction. So, this is anodic because this line is indicating the anodic one for a metal dissolution. So, this would be equal to del E by x, because this is my x and this is my del E. Now, if we consider this part, then we can convert S C equal to del E 1 divided by where this one is 1 by S A. So, equal to 1 divided by del I del E minus 1 by S A, and we can simplify and we can get del I by del E equal to 1 by S C plus 1 by S A. Now, once we know this equation, we can convert this equation with respect to the Tafel slope beta A and beta C, and let us see in case of I A equal to I 0 exponential 2.303 beta A N A neta A, which is over voltage, and beta A we have already seen 2.303 R T divided by alpha N F, and this is coming from the Butler-Volmer equation, what we have seen in the previous just a few minutes back. Now, this we can convert into over voltage, which is beta A divided by 2.303 ln I by I 0, I A by I 0. And at corrosion potential, that means if we come to this point at corrosion potential, if we would like to find out what is the slope at this point, what is the slope, and that actually passes through this small linear part, or if we consider this anodic side, that time the slope would be passing through this point, which is at E core. So, neta at a small over voltage, this we can write it as E minus E core would be equal to beta A 2.303 ln I core by I 0. This is neta A. Now, if we do the slope at I core, then it would be equal to beta A 2.303 I core, because I 0 is a constant. Now, this is nothing but S A. Similarly, we can find out for beta C, that time del E by del I for cathodic reaction, it would be beta C divided by 2.303 I core, and that time we start with beta C into divided by 2.303 ln I core divided by I 0 for hydrogen, and this is for metal. So, this is for metal. Now, from this, and here we are not considering a negative sign, because the negative sign is incorporated while considering beta C and neta C. So, from that if we do the same process, we will get this expression. So, this is one expression, this is second expression. Now, if we put that value of, and this is equal to S C, and if we have put the value of S C and S A, we can get del I by del E would be equal to 2.303 I core one, just a minute. So, del I, this would be this. So, I core 1 by beta C or beta A plus 1 by beta C, and this would become 2.303 I core beta A beta C and we can write in terms of del E del I would be equal to 1 by 2.303 I core beta A plus beta C by beta A into beta C. So, this is the expression, or we can use this expression, any of this expression. We see that whenever we have a small over voltage, then we have the slope of that over voltage versus current plot can give you the I core value, because this one we know, and if we know this, then we can get this. And what would be the experimental plot? So, we are basically plotting from this point onwards. So, actually this is my 0 over voltage. So, this is my 0 over voltage, and if we would like to find out what would be the experimental plot, then actually at this point we have to find out what is the difference between this and this. So, if we consider the difference between this line and this line and this line, then we can, because at a very we can find out a plot like this, So, the plot would be like this, and the small over voltage, this is this line, we can find out the slope del E del I, and from this expression we find out what is the I core. So, this is the concept of measuring corrosion current density from linear polarization, and this is the linear polarization curve. So, this is overall the view of or the principle of linear polarization, and of course, this is advantageous over Tafel slope, because here we do not go to a very high polarization. If we do not go to a very high polarization, what would happen? We do not get any effect from effect from resistance polarization, or we cannot get any we will minimize the effect of concentration polarization, because we are operating in a very small over voltage. Now, this linear, after this we can briefly discuss what is failure analysis. Now, this is basically the electrochemical route. So, we have discussed cathodic, we have discussed Tafel extrapolation and linear polarization. Now, on top of that there are other test methods to find out what would be the corrosion cracking susceptibility of a particular metal, and for corrosion cracking we can a method where a notch sample, this is a notch sample, we can place it in a solution and we can rotate that sample in the solution, and we can also put stress on that and then find out notch as well as pre-cracked solution, pre-cracked sample. This is basically the test for corrosion cracking. Pre-cracked sample, if we put it in solution and rotate it and after giving a certain stress, we can find out the fatigue crack, the corrosion fatigue susceptibility of the metal, and we can get a plot like stress and number of cycle. So, we can have a plot like this. Now, this is for corrosion fatigue. Then we can also think of stress corrosion, which is basically SSRT, slow strain rate test, and that case we can also determine what would be its susceptibility towards SCC or hydrogen embrittlement. So, these mechanical tests are also there in order to find out what could be the corrosion cracking tendency of particular of a material or metals and alloys in some corrosive environment. Now, we discuss the failure analysis. Once we know all the test methods, then we can also get into the failure analysis for and where the corrosion is one of the factors in the failure of engineering materials. And in case of failure analysis, we have to go step by step, and this procedure would allow us to find out reasons for failure, as well as allow us to think of some protective mechanism. And it is actually not the it is not about the judgment, only the judgment is not sufficient. We have to also find out what could be the protective routes. Now, the procedure where corrosion problem is investigated, that is actually the failure analysis in case of corrosion failure, and it provides solution rather judgment, and of course, it could be either destructive or non-destructive. Now, various stages. The first stage would be the stages of failure analysis. Actually, the first stage is getting whatever informations are available in naked eye, that those are to be collected. For example, seeing the metal magnification, the magnified glass can be used, and then we can get all the data, logbook information, specification of operation, and then we can get to know we can also observe the operation in some other in other case where the material is still working. Then we can collect samples, we can see we can also get the taking photograph of the failed surface or failed section would be very important issue. Then the second stage, this is stage 1. The second stage actually it involves collection of samples. It involves collection of samples, and those samples, collection of samples, it is it could be the material which has failed, or the rust that is there. So, that could be collected, and those should be collected in a plastic bag and should be protected properly. At the same time, let us say a material is fractured like this, this is my fracture surface. Care should be taken that the fracture surface should not be rubbed, so that the information should be protected. When we go for microstructural observation of that fracture surface, then there should be the fracture surface should not get damaged. So, actually this second stage is collection of samples. Stage 3 is basically more laboratory tests of those samples, microstructural analysis, rust analysis, and those and after collecting all the information, we can have a judgment on why the failure has happened, and finally, we can find out what are the reasons, and then what could be the protective mechanism further, so that we can prevent this failure.